Welcome back everyone. In the last few lectures we were dealing with modeling of system. Now we are at a position in this course where we know how to model a system, get the transfer function of that system. From this lecture we are going to use that transfer function to our advantage, because remember in the beginning of this lecture series itself we said that as control engineers our work is to manipulate the system so that we get the desired output. That is what we will be doing from now, using the information of the transfer function that we have. This is the point where we are actually starting what control system is. Till now whatever you were learning was all signals and systems. Today we will look into what is known as configuration of a control system. So what is a control system like? What are the components a control system is made up of? So let's get started. The first thing control system has is what is called a process or a plant. So this is the actual system that you are trying to control. When I say you are trying to control, it means you want the output to be exactly what you wish. You want the system to behave exactly as you wish. The example here can be a quadrotor. Remember the quadrotor that we had discussed? The transfer function came out to be 1 by s square, remember? Suppose that quadrotor. So in that quadrotor we took the example that the quadrotor can move only in the z direction. There is no x and y movement, only in the z direction it can move, and we found out that the transfer function of the system is 1 by s square. So in any control system problem you should always ask the first question, what is the process or plant that needs to be controlled? The second question should be, what is your desired outcome from it? If you break it down in this way, then you will know what exactly you want to do. So for example, suppose in the quadrotor example that we took, my desired outcome is that the quadrotor needs to move up, okay, to a particular altitude. Suppose it was at ground and I want it to move to say 1 meter above the ground. So the desired output or the desired outcome of the plant is that the quadrotor should move up to say z equal to 1. That is the desired output. Okay. So the plant in this case would be the quadrotor. As I say, the desired output, the desired output is nothing but reference signal. What is the reference that you are giving? Your reference is 1 meter for the quadrotor example. It can be something else also. For example, if you have a motor and you want the motor to rotate at a particular speed, suppose 100 rpm. In that case, the motor becomes your plant, that is the device that you want to control, and what is your desired signal or the reference signal? Your reference signal in this case is 100 rpm. So you want that the motor's output, which in this case, since we are talking about rpm here, in this case the motor's output say is rpm. We want that the rpm or the speed of the motor should be 100 rpm. So reference signal is the one that tells you what is the desired output of the system, of the plant. Now in order to achieve this, we will have to check what is the actual output of the system. The actual output of the system here has to be measured. Now how will it be measured? Something must be there, right? It cannot be measured, like it's not like you can see and measure things, right? Some device, some circuit, something must be there, some maybe a computer, something must be there. The device that will sense what is the output of this signal, we call that the feedback element, because it is feeding back the output. What is the output? What is the present output? It is feeding it back into the system. So this element is called the feedback element. What can be an example? In the quadrotor case, the quadrotor was supposed to move to a particular height. So what are we supposed to measure then? We are supposed to measure what is the height it is at present. Who will measure it? So we need some device, we need some sensor. The sensor in this case would be an accelerometer maybe. Okay. So or a barometer. or a gyro, some one of these sensors. So we can use a barometer, right? A barometer will give us height, we know that. So we can use that sensor. Using that sensor, we can figure out what is the height of the quadrotor from the ground. So that is your feedback element here. So the sensors are generally your feedback elements. So this part is the sensors in general, and the signal that is coming out and getting inside the feedback element is the feedback signal. These nomenclatures are important because we will be using it quite often. So the feedback signal goes inside the feedback element, it comes out, and then you can see that we have added a kind of a summer here. Okay, it is summing the two signals or subtracting. This signal, suppose it is subtracting. So this is the actual signal. The actual signal goes to the feedback element, and this is, suppose this is some y1 t, and this is y of t, and this is your reference signal r of t. Then r minus y is the error, right? Suppose in the example of the quadrotor itself, you are presently at say 50 centimeter, whereas you wanted to go to 1 meter. So the error is 1 meter minus 50 centimeter. That is the error signal, and we symbolize this with the help of a summer. It is not that every time you will have to do a subtraction. In some cases you can have a positive sign also. Sometimes you might have to add also. So we are keeping, because it is not just about one example, right? It can be used in different setups. So we are keeping it plus and minus both. So the difference between the actual position of the quadrotor and the reference position is what is called the error signal in this example, at least the quadrotor example. Next comes the controller. Now what is the work of the controller? The controller will take error signal as input, and then it will give something as output. Now what is that something? So the controller compares the reference input or the reference signal with the output and generates a control signal to reduce the error. It will try to bring down the error. Now what is the advantage in bringing down the error? If the error comes down, then your reference signal will be equal to the signal that is here. So for example, so for argument's sake, say suppose this is 1, there is nothing here. Okay, in that case this is exactly the output signal, right? This is 1, then the signal that is coming here and the signal that is coming here are both same, right? So in that case the error signal is nothing but reference signal minus yt. So if this signal goes to 0, that means RT and YT are equal, which means my reference and my output are same, and that is what we wanted, right? So in case of the quadrotor example also, you see the controller's work will be that only, that the actual distance and the reference distance or the desired distance, they should be equal. The controller, we need to design the controller in such a way that it brings down the error to 0. If the error comes down to 0, we can take care of this. Now the control output, of course, what are the types of controllers? There can be different types of controllers. The one that we are going to learn is PID controllers. There can be on-off controllers also, basically it switches on and off. We will talk about all this. Now the output of the controller goes into something called an actuator. So what is the actuator? The actuator converts the control signal. So this point, whatever signal is coming, this is the control signal. This point is, this signal is called control signal. So it converts the control signal, let me just write it down, control signal. It converts the control signal, into a physical action to influence the system. So what can it be? Again, let me take the quadrotor example. In case of the quadrotor example, you see it has to move up and down, right? How will it move up and down? It has to, if the quadrotor has to move up and down, then the 4 rotors that it has to increase its speed, so the thrust increases, right? We have talked about the basic principle of moving up and down. So if the quadrotor has to move up and down, then the thrust of all the 4 motors must increase, which means that the speed of all the 4 motors must increase. So that means if I say that supposedly that each of the motors has a controller attached to it, so basically the controller's work would be to give that exact amount of voltage to the motor, so that it rotates faster and the thing goes up, right? So in this case the motor is your actuator, because it is the motor that is converting the control signal from the controller into a physical action. Okay. So, the electric motor in the quadrotor will be your actuator, and the physical thing is basically when the motor increases its speed, the quadrotor moves up, which is the plant. Okay. So, in general this will be the setup. So, this is the output signal, this is the reference signal, this is the error signal, this is what is known as the standard closed loop system. So, these are the points you will have. In general, what happens is these two, actuator and process, we generally consider them together as the plant. The process and the actuator together we consider them as the plant, because you see in the case of the quadrotor itself, I mean separating out the motor from the quadrotor and analyzing them becomes much difficult. So, what we can think of it is that the entire thing is one setup, and that is what the plant is. So, this also can be called as a plant, but in general the actuator we take into the process itself. So, this will be your plant from now. So, this is the basic structure. So, you must have a plant, you must have a feedback element, and you must have a controller. Controller is the one which is your responsibility. You are supposed to design the controller. Okay. So, now that we have gone through this series of lectures and classes, we already know that once we have this setup, we can just bring it to pen and paper mathematically, right. What we have to do is we have to just find out the transfer functions for each of them. So, the plant will have its own transfer function, the feedback element will have its own transfer function, and the controller, which is our responsibility, okay, that will also have its own transfer function. In general, when the feedback is not there, the system without any feedback is this, simply this, u of t and y of t. And till now whatever we have learned, we have already learned how to find out GS and all that. So, we already know that yt and ut are related by GS by y equal to g into u, right. So, all those relation we know, for each system we know how they behave or what is the relation. So, using this mathematical modeling, what we can do is we can think we can convert this into transfer function. So, the plant is a transfer function now, the feedback element is a transfer function now, and the controller Ks is the transfer function that you have to find out so that the system behaves as you want it to behave. Okay. So, this is the basic setup. Now, if this is the basic setup, at the end what we will try to do is we will just want to convert this entire thing into one. So, this entire thing, if we can take this entire thing and make into one block, basically bring everything together somehow mathematically, we come up with a combined transfer function which relates y and r. Then we will have something called a closed loop transfer function. Remember, this system is actually built up with different components, right. This is the standard closed loop control system, okay, standard configuration. So, in this standard configuration you have a controller, you have a plant, you have a feedback element. Out of this Ks is the one that we want to design. So, what we can do is we can actually go ahead and club them together and make it into one transfer function, one big transfer function, big not like mathematically, it is a big just as a word, a closed loop transfer function, and this transfer function relates y and r. Now, as you change Ks, this transfer function will also change, right, and your y and r's behavior also changes. So, you have to come up with that correct k that will give you the behavior that you want to do. This is what mathematically we have to do for design of a controller. So, our purpose of this course is to design a controller so that we can get our desired output, and in this case this is the one, this is the part that we can change. These and these are fixed, this is given to us, these are fixed, you cannot change that. This is the part that you can change, and now what to put there, what kind of transfer function should I put there, that is what we have to discuss. So, this is the overall configuration, this is the standard closed loop system that we are going to operate on for the next few lectures, and in the next class we will take GS to be some standard transfer functions and we will see how they behave, and in most part of this course we will consider this to be 1, considering that the output is directly fed back into the system. Okay, we are not taking a standard feedback element here. We can do that, but there are ways to remove that. So, we will talk about that also, but for the time being what we are going to do is we are going to consider what is called a unity feedback configuration. What is a unity feedback configuration? In a unity feedback configuration, the HS part here is 1. Okay. So, in a unity feedback configuration we are going to work, and later on I will show you in general, if you have this setup, how to go from this setup to that unity feedback configuration. So, if you know how to go from this setup to the unity feedback configuration, then you know whatever we are going to study we can apply, and then again later on you can come back to the original system. Okay. So, I will end here today, and then from the next class we will start looking at mainly into two different types of plants, standard plants, so that we know how to design controllers. Thank you.